Okay, so today I'm going to go over how to calculate the big theta for some t of n examples. So first, for this equation, t of n equals n cubed minus 2n squared plus 1, we first want to look at the largest term. In this case, since t of n is a polynomial, we know the largest term is going to be the highest degree term of the polynomial, so n cubed. And we want to prove that t of n is theta of n cubed. So and it is theta of n cubed if it is both O of n cubed and omega of n cubed. So to prove this, we're going to prove that t of n is O of n cubed and omega of n cubed. Okay, so let's first start by proving that it's O of n cubed. So O n cubed. So first we want to choose our constants. So for O of n, generally it's easiest if we choose a constant that's greater than n cubed. In this case, I think it's easiest if we choose a constant that's greater than the constant in front of n cubed. In this case, 1. In this case, 1 would work, but it's usually easier to choose a greater one. So I'm going to choose 2 for our constant. And previously I said that we can find our n naught by setting c times f of n equal to t of n and solving for n. I realize now that that's not a good approach for finding n naught, and that's because there's like two instances where it's difficult. The first instance is if the equation is not solvable, so not all equations intersect. So there will be some cases where c times f of n equals t of n has no solutions. And the second case where it's not a good idea is if the equation is just difficult to solve. So I'm going to approach finding n naught a little bit differently for these examples. So what I'm going to do is first I'm going to write the expression that we're trying to prove, which is 2n cubed is greater than or equal to n cubed minus 2n squared plus 1 for all n greater than or equal to n naught. And we're not going to define what n naught is yet. We'll wait to first simplify this equation as much as possible before deciding which n naught to use. So to simplify this equation, we can subtract n cubed on both sides, and we get n cubed is greater than or equal to negative 2n squared plus 1. And then we can move the 2n squared over. And so now from this expression, we know that n cubed and 2n squared will always be positive for n greater than 0. And if we just choose a simple, let's say n is equal to 1, or n is greater than or equal to 1, we know that n cubed will be greater than or equal to 1, and we also know that 2n squared will be greater than or equal to 1. So in this case, I'm just going to choose my n naught as 1. And then with an n naught of 1, we can easily prove that this statement above holds true for all n greater than or equal to 1, because n cubed is greater than or equal to 1 for all n greater than or equal to 1, and 2n squared is greater than or equal to 1. For all n greater than or equal to 1. And so therefore the sum of these two terms would also be greater than or equal to 1. This is good enough to show that t of n is O of n cubed. and now we want to show that it's omega of n cubed. So for omega of n cubed, we want to choose a constant that's going to be less than the constant in front of our largest term, our f of n. In this case, that constant is, that coefficient is 1 over here, so we're going to choose a c-value of 0.5. And then we're going to go through the same process. We're going to write our statement that we're trying to prove, which is 0.5 n cubed is less than or equal to n cubed minus 2n squared plus 1. For all n greater than or equal to some n naught. So the difference between O of n and omega of n is just one is you're choosing a c value that makes f of n a lower bound for t of n, and in the other case you're choosing a c value which makes this expression an upper bound for t of n. But other than that, the proof is identical other than the inequality. So once again, we're going to approach finding n naught the same way by first simplifying the expression to a term where it becomes sort of obvious what to choose our n naught as. So I'm going to subtract this 0.5 n cubed and we have 0 is less than or equal to 0.5 n cubed minus 2n squared plus 1, and I'm going to move the 2n squared to the other side. So 2n squared is less than or equal to 0.5 n cubed plus 1. And so what I was mentioning before about some equations are difficult to solve, if you notice this expression, it's kind of not obvious how to solve it, but if we remove the 1 over here, it becomes very simple to see which n naught would work. So what we're going to do in this case is if we prove that 0.5 n cubed is greater than 2n squared, then we will also know that 0.5 n cubed plus 1 is greater than 2n squared, because we know that 0.5 n cubed plus 1 is greater than 0.5 n cubed. So we can essentially simplify this expression to say that 0.5 n cubed is greater than or equal to 2n squared. And temporarily we can ignore this 1, because if we prove this statement, then trivially we've proved this statement as well, because 0.5 n cubed is less than 0.5 n cubed plus 1. So this statement's much easier to show because we can cancel out the n cubed with the n squared, and we get 2 is less than or equal to 0.5 n for all n greater than or equal to n naught. And then by looking at this equation, we can see that a suitable n naught for this expression would be an n naught that's at least 4. So we'll choose n naught equals 4. And then we know that whenever n is greater than or equal to 4, 0.5 times n will be greater than or equal to 2. So from this we've proved that t of n is omega n cubed. And since t of n is both O of n cubed and omega of n cubed, t of n is theta of n cubed. So that's basically the process. I'll go over another example. But essentially, the process is you start out with an initial statement, which is the definition of either O of n or omega of n. So if you look at this statement, this is what we're trying to prove. And then we can simplify this expression, because simplifying the expression doesn't change its like truth value, so to speak. And once we've proven it for the simplified expression, it will prove that it holds true for the non-simplified expression. So let's look at another example. T of n is equal to 2n log base 2 of n plus 3n minus 1. So in this expression, we need to find the largest term again. So we have a linear term, a constant term, and this term over here, which is n times log base 2 of n. And we know that log of n is greater than a constant. It increases. It's a function which increases. So n times log of n will be greater than a linear term. So our greatest term is n log n. So we are going to prove that t of n is theta of n log n. And I'm not going to write the base, but all of these logs are base 2. So we'll start out by proving O of n log n. And so first we want to choose a suitable c value. So once again, the coefficient in front of our f of n is 2. And so for O of n, we want to choose a c value that's greater than our coefficient. So I'll choose c equals 3. And then we'll write down our definition of O of n, which in this instance will be 3n log n is greater than or equal to 2n log n plus 3n minus 1. And then for all n greater than or equal to n naught. So once again, let's simplify this expression as much as we can. We can subtract the 2n log n on both sides, and then we get n log n is greater than or equal to 3n minus 1. And then once again, we run into the same thing that we ran into in the last example, where proving that n log n is greater than, or simplifying n log n is greater than or equal to 3n minus 1 is more difficult. But we know that if n log n is greater than or equal to 3n, then it must also be greater than or equal to 3n minus 1, because 3n is greater than or equal to 3n minus 1. So by proving that n log n is greater than or equal to 3n for all n greater than or equal to n naught, we've like implicitly proven that it's also greater than or equal to 3n minus 1, since we can easily show that 3n minus 1 is less than 3n. So in this expression, we can cancel out the n's, and we have log n is greater than or equal to 3, and then we can raise each side to the power of 2, and so we have n is greater than or equal to 2 cubed, which is 8. And so in this case, we'll choose an n naught, which must be greater than or equal to 8. So we'll choose n naught equals 8. And so then for all n naught greater than or equal to 8, n will be greater than or equal to 8. So t of n is O of n log n. And then we'll look at the omega case. So we'll show that it's omega of n log n. And so we want to choose a c value that's less than our coefficient in front of our f of n. So our coefficient's 2. We'll choose a c value which is 1. And then we'll write down our definition for omega for this instance, which will be n log n is less than or equal to 2n log n plus 3n minus 1. And then we'll subtract this n log n from both sides, and we have 0 is less than or equal to n log n plus 3n minus 1. We can move the 1 to the other side. We have 1 is less than or equal to n log n plus 3n. And then in this case, I'm just going to look at, let's see, we'll look at, if we take n is equal to 1, then we know that this term will be greater than or equal to 1, and we know that this term will be greater than or equal to 0. So the sum of the terms will be greater than or equal to 1. So for any n greater than or equal to n naught, we can set 1 as our n naught, and for any n greater than or equal to 1, this expression will be greater than or equal to the one that's on this side. So we'll choose an n naught of 1, and then essentially 1 is less than or equal to for all n greater than or equal to 1. And if you want to simplify this further to prove it, you can do what I was doing in the other two examples, where you know that since n log n is a function that's always greater than 0, if 3n is greater than or equal to 1, then 3n plus n log n will therefore be greater than or equal to 1, because n log n is greater than or equal to 0. So you can actually simplifying it by just you can actually simplify the proof by just saying 1 is less than or equal to 3, and then this is pretty clear that 3n is greater than or equal to 1 for all n greater than or equal to 1. So t of n is omega n log n, which means that t of n is theta of n log n.